Any other guesses? Haha, yay. All right. Did y'all see my email last night about the typos?
Yeah.
Okay. Yeah. Sorry about that. Especially the one about the missing answers, because it was obviously supposed to be a multiple choice one and there were no choices for you to pick from. So that's a problem. We got Kyle. Ew. He's bleeding on me. Okay. There. Okay, so here we're talking about double integral some more. And then we'll do triple integration. And then coming up after that is going to be applications. And is that it for this chapter? Oh, no, change of variables. Well, that's the thing. Oh, yeah, we're going to get to the Jacobian stuff. Yay. So, yeah. So it looks like that we will be able to get to some, maybe, the theorems. And we'll see how that goes. All right, so, oh, there's a big bug in here. So we're going to be talking about properties of double integration. So one of y'all CPAs had to deal with vertically and horizontally simple. So it says a region is vertically simple where you have an upper and lower bound for your x and an upper and lower bound for your y. That if I'm looking at it this way, I would be integrating with respect to those bounds and then integrating with y and then dx. But the horizontal would be where I'm bounding the y's and then the x is according to it being a function of y and then integrating with respect to x and then y. And so what those pictures are saying is, so if I am vertically simple, so they drew this picture. And then created these bounds. They kicked me out. Is everybody there?
Yeah, you.
Yep.
Okay, yeah, I got kicked off for some reason. I don't know what happened there. Oh, and AJ's here now. So I'm just missing Michael and Joe. Kramer. Okay, so if I'm looking at that, I'm going to be looking at, so here is going to be A, B.
It does not want us to learn today.
What is
Yeah, we can't even see her actual screen.
I hear y'all. Do you hear me? Hello?
Well, it's not everyone's like favorite thing, but some people enjoy it.
Some people are wrong. It's okay.
I'm decent at it. I just don't like it.
Okay. Y'all see me?
Yeah, tonight.
Yes.
Okay. Apparently, having the TV on.
Sorry, traffic was terrible,
Shut up,
but I'm
Angelo.
here.
You missed the joke and of course all of our troubleshooting problems I'm having.
Oh darn. Whatever shall I do?
Now, your whole day should be ruined now.
It is, irreparably.
All right, let's try this again. All right, so are we there? Everybody see me? Everybody sees this screen?
See.
Okay, all right. So there's your A,
Got scared of me.
and this is gonna be G2 of X. This is gonna be G1 of X. So we have this upper and lower bound for the Y's. And we'll be looking at the integration along those vertical lines, and we'll add all those up. Of course, like when we do how it integrals the sum of these lines. So that's what's going to be doing there. But with horizontally simple, you're looking at it this way. This is going to be C. This is going to be D. And this is going to be G1 of Y, G1 or G2 of Y. And I have these bounds. And I'll be looking at it. Oh, that should be dotted. In that direction. So here you have the vertical, there you have the horizontal. So that's what that's saying there.
Could we technically, for horizontally simple, also use X instead of Y?
Well, because then if you mean like this way, like this
Well,
is X and this is
just
X.
like, because if you're looking at a three-dimensional figure there, your Z will always be like in the vertical direction, but your X and Y will just be in differing horizontal directions.
Yeah, but right now we're just looking at X and Y. That plane. So it's
Oh,
that,
all right.
right? So down. So you have the change in X's and the
Oh,
Y's.
all right, that makes sense.
All right. Okay, so let's try looking at a concrete example where we're going to evaluate this double integral over this domain, where this domain is going to be bounded by this region where y is equal to square root of x, y equals 1 over x, and x is 3. So if I drew a picture of that, it's a different color. So here is those functions. Let's do blue. And then there's 3. So I am looking at what color? Let's do regular. That's black. What else different colors? Pen. Nope, you're dead. Light colors. I want there. So we're looking at that region. And then I need this bound here. So what is that number going to be? Where are those two functions equal to each other?
Where 1 over x is equal to root x. Is it not where you set root x equal to 1 over x?
Yeah, but what would that number be?
Oh, you
1.
actually want us to find it. Okay. 1.
Is that what you said, Julie?
That's what
Yeah.
Julie said, but louder.
Hey, all right. So we see our bounds. X is going to be between 3 and 1. And we have y is between. So who's going to be the lower function?
1 over x.
And then my upper would be that one. So now this means that we are describing D as vertically simple. Does that make sense? So now all we have to do is set up the integral. So we have,
So we're setting it as vertically simple because there's functions bounding it.
yeah,
Okay.
the way that the functions were described to us, that helps us figure out how this integral is going to end up being set up. Does that make sense?
Could we, like, if we wanted to, could we make it so that it would be horizontally simple?
So then that would mean that we would have to
It's gonna be
change
a
this
whole harder.
as a function of y then. So that would mean x equals y squared, and x would equal 1 over y. And then you would have to graph those functions and see where those bounds are.
So you could, it'd just be really difficult.
You're just adding more work to yourself, I think. So yeah. And this is definitely something we easily see, right? As opposed to this kind of flips how we're supposed to view that function if we go with the horizontally simple. right? So now that we described it as such, we know the outside one is going to be 1 and 3. And then the inner one is going to be 1 over x root x of that dy dx. All right, so y'all find that integral for me and see what we get. Pause so I don't give you my answers. Oh, what happened there?
Increasing. Decreasing.
Did y'all get an answer yet?
I'm still working. I made a mistake and am trying to fix it.
Okay.
Real quick, what section are we in?
15.2?
15.2. Okay. Thank you.
Yeah, I'm not getting what the answer from the book got.
I did everything in my head and got 3/4.
No, it should be a number.
That is a
I got
number.
9.
Like a nice, pretty number. Who got
Oh.
9? Taylor, you got 9?
Yeah.
Okay. I'm getting 7. I'm subtracting 1 instead of adding 1.
I got 9 as well.
What am I doing?
Mm.
That's what I'm doing wrong.
All right, well. Here. So did y'all get this part when you did the inside integral? Yes, no?
Yeah.
Yeah, okay. Then you integrate this guy, and you should get this, right? Then when I plug in that part, see, that's where I get -3/2 plus 1/2 should be -1. Oh, that's a 10. Oh my God. I was thinking that was 8. What is wrong with me? Now that should be 9. Oh, okay. Obviously, I cannot divide 8 into 80. There we go.
Did you freeze your screen?
Oh, yeah, it froze again. Sorry. Let me get it off of that button in case it clicks on there. So, did y'all get 9 now?
Let's see.
Okay, cool.
No, but I'll figure it out eventually.
What did you get, Julie?
I'm still working on it. I have made a mistake in my integration and I'll have to.
The first one or the second one?
The first one?
Okay. So did you get this?
I got x² y² over 2, yes. And then
Plug those in.
and then I made mistakes.
Okay. So watch our algebra. So then this ends up being 9. Did I not do this one? No, I didn't do this one. Actually, let's look at this one. Piece of paper. There we go. Let's look at example 3. So it says, find the volume of the region between the plane z equals 2x plus 3y and the triangle in figure 8. So the figure that we're looking at is, if we look at the x and y, so this is a triangle that they're talking about. We're looking at this, right? And then we're also looking at the volume of this thing that's bounded by this 2x plus 3y. So it ended up looking like we're looking at kind of looks like a pyramid. So we're trying to find the volume of this pyramid, and this triangle here is that guy's base that it's laying on. So here's y equals x over 2. That's going to be y equals x on this piece right here. Does everybody kind of see that, where this triangle's there? Yes, no?
Yes.
Yeah.
Okay, cool. Alrighty.
So
So,
this one's horizontally simple.
yeah, so this will be a horizontally simple one. So if I be looking at this as a volume, so the volume, let's use not light pink because that doesn't necessarily show up very well. So the volume is gonna be, cat, stop doing that. So that's the general formula. So I know I'm going to have two integrals. So I see here that my y is bounded between 0 and 2, and x is bounded by, if so we remake these as functions of x. So this one stays the same, but this one would translate into x equals 2y. So my lower one is going to be y, and the bigger one is going to be 2y. So this is horizontally simple, like Josh said, right? Josh, did you said that?
Yeah.
So then my outside is going to be 0 to my inside is going to be y 2y. And the function I put here is that, a function of x and y. So that'll be 2x then dx dy. All right, let's try this one. It's going to give me x squared plus 3y. Is that what y'all got for the inside one?
Yes.
Cool. All right, and then outside. Does that make sense?
Yep.
All right, and so that would be cubic units, whatever our units are. But I'm curious if I could actually then use the volume for a pyramid and actually make sure that I do get 16. Which means I would have to figure out the area of the base. Technically have the height. That'd be interesting to make sure that we get the same thing. That would be neat. Because it would be 1/3 the area of the base times the height. And that would hopefully give me 16. I'm going to have to do that and see if that's... Because I just taught this in one of my other classes, is finding volumes of pyramids. So I think that would be fun. All right, cool. Now, since y'all did bring this up, I wasn't going to go over this problem, but now I think we should. So, choosing whether or not to look at it as vertically simple or vertically horizontal.
Horizontally simple.
Yeah. Thank you. A little out of it today, sorry. So let's look at example 4. So I want to figure out this integral over this domain of e to the y squared dA for d is this the region. And then we are going to look at it as this triangle. I'm going to draw my graph. Let me bring there's the green one. This is a line y equals 2. And then so that region, right? So if we look at the values here, so this is going to be 2, this is 0, and then what is this x value going to be? What value of x would make this number 2? Make y
4.
4. All right. So if we look at it as vertically simple, x is going to be between 0 and 4. And then y is bounded by the lower function being x over 2 and the upper function being 2. Now, if we look at it as horizontally simple, that would mean y is going to be between 0 and 2, and x is going to be bounded by the upper function being
X equals 0.
0. And what is the one above that?
2y.
Is it y or is it going to be
2y.
Would it be 4? No, 2y. There you go.
because we want it to be a function of y, right? So this is going to be a little where the wonkiness comes in, right? So if I'm looking at it horizontally simple, my x is bounded by x equals 0, so that vertical line, and then this line that's changing, which is going to be that x over 2 line, right? So technically I'd be looking at it like that. So here's that vertical line, x equals 0, and then my upper function is going to be this linear line, or this linear function, y equals x over 2, but I want it as a function of y, so I would solve for x in that equation. Does that make sense?
Oh my God, there's a cat.
So that's where that upper bound is, that one. So now if we look at that, so if we look at the vertically simple, that would mean that I would be looking at the iterated integral of ey squared, and then it'll be dy dx. Y would be the x over 2 to 2, 0 to 4. So that would mean I would want to integrate this first part, right? E to the y squared dy, evaluated from x over 2 to 2. Can we integrate that?
Freaking no.
No, we don't have a nice way of doing that, right? Unless we use Mathematica. Right? But if we look at it through the horizontally simple now, so now this one might give us a little bit. So that would mean I'm still looking at now I'm going to switch it to where I'm looking at dx, dy. So that would mean my inside would be 0 to y, and then my outside bounds are 0 to 2. So when I integrate this guy, that means that all I need to do is put in an x there. Now that's going to give me 2y e to the y squared minus 0, which is 2y e to the y squared. Now I'm going to integrate the outside part. Now this can be integrated, right? Because that would just be u substitution. Y'all see how that's u substitution?
Yes.
So what's my u?
Y squared.
Right? So that means du is going to be 2y dy. So in general, this integral can be written as e to the u du, which is just e to the u plus c. So that's just going to be 4 e to the y squared plus c. So if I have it with the definite bounds, that's just going to be e to the y squared evaluated from 0 to 2. So that's going to be e to the 4 minus 1.
Much simpler.
Yeah. Not frightening at all.
So basically, it's sometimes easier to look at it horizontally instead of vertically.
Right. Sometimes, yeah.
Gotcha.
Just based on how the integral is going to be set up. And then sometimes it might be easier to look at it vertically just based on how the functions are. So
Can you go up to the top real quick? Okay, it was e to the y squared.
does that make sense? And everybody got it before I take it away?
Yeah. It's on recording.
Yeah. Well, what's wrong, Angelo?
I was just slow at writing things down.
Oh, okay. Do you need this?
Yeah. You know what? I'm just going to take a picture on my phone.
Yeah, I just want to make sure that y'all are getting it because I lost one of the lectures and I still have not been able to find it. So, and I think it's the one you missed, Julie.
Yeah.
Sorry.
All right, I'm good.
You got it? Okay.
I got a picture.
I just want to make sure y'all are getting it. For those of y'all who are there, at least have that chance. All right, and then the rest of the section was mostly like formulas and facts and stuff, and then there was some estimation, and I don't like estimation, so we're not gonna do that. So we also have these properties. So if f is a function that's less than or equal to some other function g, then we would say that the integrals over those domains keep that inequality. That's there. If we have a function that's bounded by these two numbers for all the elements in its domain or that region, then m times that area is going to be less than that area, less than m, the big M times the area. So, and then this leads to the idea of developing what's called the average of a function. So do y'all remember that in Cal 1 we were talking about the average value of a function, and we had 1 over b minus a integral of f of x dx. Y'all remember that? That was back in, I just found it last night. Where are you? Monotonicity. I want it where we were talking about antiderivatives. There we go. I should have put my bookmark there. I don't know if there I can't find it. I'll have to find it. There's the net change. Oh, it's not here. No, it has to be here. I'll find it later. But yeah. So, and then that leads into the mean value theorem. So that was something y'all talked about, right? In Cal 1.
Yep.
Yeah. And then they also the book used this F bar notation, which means average, right? I don't know if any of y'all taken statistics, but like X bar represents mean of a data set. So that's
Yes.
what bar notation means.
That makes a lot more sense now.
Why they use the bar.
Yeah.
Then,
Just like what it meant. Like I knew the bar meant mean, just I didn't make that connection.
so yeah, and then got some homework problems there, and then we have triple integrals coming up next, but that'll be tomorrow.
Oh, yay.
Yeah. I will also write a quiz for this as well too, so that way, because we're on quiz. What number now? 9?
10.
10?
We
Okay.
did 9.
Oh yeah, which reminds me. So some of y'all have sent me some very
Interesting.
sympathetic sounding or sad sounding. Me being sympathetic.
Pathetic sounding is about right.
Not pathetic. No. If your quizzes and CPAs are like a day late, that's not going to be a big deal. Because like sometimes we have internet issues. Obviously we had them this morning. Just don't make it a week late. So. Okay, Angelo?
Yeah, I keep seeing it on the calendar as due the next day because
Wow,
it's
call
at
them
like
out.
the midnight right there. So
Yeah.
I do it that day, but like that's a day late for some reason.
So yeah. Yeah. If it's a day, maybe 2, not a big deal.
Hmm.
Okay?
Got it.
So, because obviously I keep on top of everything and do everything in a timely manner. So
Immediately. The second it's turned in, you're
Yeah.
grading.
does not happen.
That's the deal.
All right, guys. Well, I will have office hours later if you need them. I will be here, assuming I don't get kicked off the internet. And I will see you guys tomorrow, okay?
Horizontal.
Adios.
All right, bye,
Sweet.
guys.
Bye.